What's up, everybody? Today we're going to talk about interpreting change in exponential models. It's a lot of words, but don't freak out because we'll just read them and they'll figure it out. So, Elon sent a chain letter to his friends asking them to forward the letter to more friends. The relationship between the elapsed time t and days since Elon sent the email and the total number of people who received the email, P of t, is modeled by the following function. P of t equals 4 times 3 to the t power. Complete the following sentence about the daily rate of change in the number of people who receive the email. So let's take a look at more closely what it's saying. It's saying that we have a couple things here. T, we're going to measure in days. P of t, this is just a notation. This is another way to say y. P of t, like my total, like y equals mx plus b or something. P of t is another way to say y. It says that my function, I'm going to call it p, is controlled by t. I put a t value into my function and I get my y value out. And in this case, I pick p for people. Basically, it's a name of a function, so you can refer to it. So this says p of t equals 4 times 3 to the t power. This is an exponential function because I have a variable that's an exponent. So that's why it's called an exponential function. Exponential functions usually look like y equals a times b to the x power. Okay, where these two are actual numbers and these two stay integers. Sometimes this is x, sometimes it's t. Sometimes this is y, sometimes it's p of t. Okay, so a is what I start with. B is my change. Could be in percent, or it could be a factor. Okay, and in this case, factors are easier. In this case, it says every day the number of people who receive the email grows, shrinks. So I got to pick either grows or shrinks by a factor of blank. So super easy. If b is bigger than 1, right? So b is larger than 1. It's supposed to be 1, not an L looking thing. Look better without all the scribbles. When b is greater than 1, then it grows. If b is less than 1, it shrinks. Now b will also be greater than 0. Greater than 0. So, and if b equals 1, doesn't do anything. Stays the same. Okay, so let's take a look. b is 3. That means this grows. By a factor of, when it says factor, just take this number. And that's going to be it. So let's take a look at a couple more, see if they're really hard or not, okay? So, when Zakir threw a beach ball to his friend, its horizontal velocity, like how far it's traveling horizontally, changed as it traveled through the air. The relationship between the elapsed time t in seconds since Zakir threw the ball and its horizontal velocity, v of t, in centimeters per second is modeled by the following function. So, just to explain what's going on, Zakir's throwing a ball. I can calculate its velocity by figuring out how much time in seconds it's been since he threw the ball. And so if I want to figure out how fast it's going after 2 seconds, I put 2 in for t and I do my math and it'll tell me how fast it's going in centimeters per second. All right, so let's take a look at this again. Every second the velocity of the ball grows or shrinks. Well, remember what we said. Take a look at my b term. It's 5/8. 5/8 is less than 1. That means this puppy shrinks. By a factor of, when it says factor, it's super easy. I just take b by a factor of 5/8. Marcus sent a chain letter to his friends, asking them to forward to more friends. The relationship between the elapsed time t in days since Marcus sent the email and the total number of people who received the email, P of t, is modeled by the following function. P of t equals 6 times 1.43 to the t power. So, once again, I can calculate how many letters are sent to people, or how many people received a letter by this function. After 1 day, it would be 6 times 1.43 to the first power. After 10 days, 6 times 1.43 to the 10th power. So complete the following statement about the daily percent change. This is where it's a little different, right? Last time was factor, now it's percent change of the number of people who receive the email. So when it says percent change, we got to do a little trick here. It's not that much harder, trust me. First of all, take a look at my B term. It's 1.43. So do I add to the number of people that receive letters or subtract? Same rules. If it's greater than 1, I add to. If it's less than 1, then I subtract from. So 1.43 I added to. Blank percent. So this doesn't say factor, so it's a little different. So all you have to do is you have to take my B term, okay, and subtract 1. And actually, it's going to be the absolute value of that. Remember what absolute value means. Turn your answer positive no matter what. So if I do 1.43 minus 1, I get 0.43. Now that is a percentage, but as a decimal. I want the percent as a percent though. So to turn it into a percent, I have to move this thing twice and make it 43%. So every day, 43% of people are added to the total number of people who receive the email. All right, last one. I think we got this. On the first day of spring, an entire field of flowering trees blossoms. The population of locusts consuming these flowers rapidly increases as the trees blossom. The relationship between the elapsed time t in days since the beginning of spring and the total number of locusts L of t is modeled by the following function. L of t equals 1200 times 1.65 to the t power. So day 1, it's going to be 1200 times 1.65 to the first power. That's the number of locusts. Day 100, 1200 times 1.65 to the 100 power locusts. So complete the following sentence every day. Let's do the easy one first. 1.65, that's bigger than 1. That means we added 2. We want to know percent. So I do 1.65 minus 1. Gives me 0.65. Turn that into a percentage though, and it's going to be 65%. So hopefully this is pretty easy now. And if you have any problems with it, let me know.